Hey everybody, my name is Calvin and welcome back to my channel. Today we're going to be talking about decision trees. We'll learn about decision trees and how they work in Python. A decision tree is a machine learning model that makes predictions by breaking a problem into a sequence of smaller decisions. Instead of learning one question like linear regression, a decision tree will learn a set of questions from the data, and each question splits the dataset into groups that are hopefully easier to classify or predict. Think of a decision tree like a flowchart. At the top, the model asks its first question. Based on that answer, the example moves left or right. Then the model asks another question, moves again, and keeps going until it reaches a final stopping point, which is called a leaf node. Then the model asks another question, moves again, and keeps going until it reaches a final stopping point called a leaf node. For example, if we are trying to classify flowers, the tree might ask whether the petal length is less than a certain value. If the answer is yes, then the flower goes down one branch. If the answer is no, it goes down another branch. Later, the tree might ask about other features like petal width. After a few decisions, it helps us predict what flower it is. What makes this really useful is that we're not manually writing every single rule ourselves. The algorithm's designed to look at the training data and choose the splits that best separate the target classes. In a classification problem, the tree is trying to create cleaner groups, meaning groups where most examples in that group belong to the same class. And that's what makes decision trees different from models like linear regression. For example, linear regression tries to fit a straight line relationship between inputs and the numeric output, while decision tree does not need that relationship to be such a straight line. It can help us really capture more flexible patterns because it separates the data step by step. What can decision trees be used for? They can be used for both classification and regression. In classification, the goal here is to predict a category, like whether email is spam, whether a customer will churn, or what species a flower belongs to, like we talked about. In regression, the goal is to predict a number, like a house price, sales amount, or delivery time. Here, the basic structure is pretty much the same in both cases. Our decision tree will ask questions, follow the branches, and then finally reach a prediction at a leaf node. Decision trees serve as the foundation for random forests. A random forest is built from many decision trees, hence a forest. A single tree is easier to understand and visualize, but it can be unstable. A random forest will combine many trees, so the final prediction is usually stronger and more reliable, although the model becomes harder to explain as one clean set of rules. In this video, we're only going to mainly focus on a single decision tree. We have to understand what a single tree is before we move on to random forests. Before we actually start coding, we have to make sure we import the correct packages. First, we're going to be importing pandas so we can work with the dataset as a table. And it makes it easier for us to view columns, inspect first few rows, and understand what each row represents. Then we'll import matplotlib to help us visualize the decision tree later. Then we're going to import scikit-learn. Here we're going to get our dataset, the train test split functions, the decision tree classifiers, and a few tools for our evaluation. We're going to be loading our dataset. Our dataset here is called Iris. The Iris dataset is a classic machine learning dataset. Each row here represents an iris flower, and each flower has 4 measurements: sepal length, sepal width, petal length, and petal width. And here, our goal is to predict the species of the flower. There are 3 species in the dataset: Setosa, versicolor, and virginica. Here we store the input features in the variable x, and those will serve as the measurements that the model will use to make predictions. And here the variable y will contain the target labels, which are the correct species for each flower. We'll run our block of code here. Let's turn this data into a data frame from pandas. What this will do here is give us a table where each row is one flower and each column is one measurement. Then we add the species label as the final column. We can call head on this data frame here, which will show us the first 5 rows, which is a quick way to confirm that the data loaded correctly. And here we see that we indeed have our 4 features: sepal length, sepal width, petal length, petal width, and the species. Right now the species column is numerical. Those numbers here will correspond to the actual species name. We should also check the size of the data frame. We can do that by printing the shape of the data frame. Here we have 150 data rows and 5 different columns, which correspond to our 5 columns from above. Before we train the model here, we need to separate the features from the target. The variable x contains only the feature columns. We want to remove the species column because that is the answer we want the model to predict. The variable y contains species labels, and that gives us the standard supervised learning setup. Features in x and the correct answers in y. Now, we split the data into training and testing sets. Here we have x train, x test, y train, and y test. The training set here is used to teach the model. That's how the model is learning. The testing set is held back so we can evaluate the model on examples that our model did not see during training. We've set the argument's test size to 0.2, which means that 20% of the data goes into the test set. This random state will help us make sure we can reproduce this specific model later, and stratify here will keep the class proportions balanced across the training and test sets. Since this dataset has 3 species, we want to make sure both sets contain a fair mix of each class. Now, we want to create the decision tree. We're going to be setting our variable tree to an object called decision tree classifier. The most important setting in this decision tree classifier is the max depth. We've set that to equal to 2. Depth here controls how many levels of questions the tree is allowed to ask. A tree with depth 2 is small, easy to understand, and less likely to overfit, but it may not capture every single pattern in the data, meaning your decision tree is going to be underpowered. The next line here, tree.fit, will train the model. During training, the tree looks for feature thresholds that split the data into cleaner groups. In classification, a cleaner group means most of the examples in that group belong to the same class. Let's run this, and here we get this fun little output here from scikit-learn. In the parameters sections, you can see the values that we set ourselves, like max depth and random state. You can also see the default settings that scikit-learn filled in for us. For example, criterion equal Gini means the tree is using Gini impurity to decide which splits are useful for us. The setting splitters equal to best means the tree is trying to choose the best available split at each step. You also see things like min samples split is equal to 2 and min samples leaf equal to 1, which control how small the tree is allowed to make its groups. Below that, you'll see fitted attributes. The fitted attributes here are values that only exist after the model has been trained. For example, classes shows the class labels the models learned. In this case, there's 0, 1, and 2, for the 3 iris species. Feature importance values show which features the tree relied on most when making its splits. In your output, the first 2 values are around 0. The petal length and petal width values are much higher, which means that this particular tree mainly used petal measurements to separate the species. You'll also see feature names in. This confirms the names of the columns the model was trained on, and n features in, which tells us the model used 4 input features. Now on to the fun part. Let's make some predictions. Our predict method here will send each test example through the tree that we just created. Each flower starts at the top of the tree, answers the first question, moves left or right, and continues until it reaches a leaf node. And then that leaf node will give us the predicted species. And we can see the predictions that our model made. Remember that each one of these will correspond to a flower species. Let's compare the predictions with the actual labels. The table here shows the true species and the predicted species side by side. Here we can see we have a very good accuracy. Using the head here, we see that the first 5, we've correctly predicted the correct species. That only gives us a sneak peek though. Let's take a look at the accuracy. The accuracy here tells us the percentage of test examples that our model classified correctly. We see that accuracy is around 93%, which means that the model got around 93% of the test examples right. Accuracy is a good starting point here because the iris dataset is fairly balanced, but it's still useful to look at more detailed metrics. The classification report here helps us see the precision, recall, and F1 score for each species. What do those metrics mean? Precision tells us how often the model is correct and when it predicts a class. The recall tells us how many real examples of that class this model successfully found. F1 score combines those two ideas into a single number. Take a look. Now let's go through our results. For the Setosa species, the precision, recall, and F1 score are all 1, which means that the model handled that class perfectly in this test set. Every flower predicted as Setosa really was a Setosa, and it found every actual Setosa example. For Versicolor, the precision is 0.9, the recall is 0.9, and the F1 score is also 0.9. That means the model did well, but it made at least one mistake involving this class. It either predicted Versicolor for a flower that was not Versicolor, missed a real Versicolor flower, or both. And the same thing happens here with Virginica. Here we see the overall accuracy is around 93%, which means the model correctly classified 93% of the 30 test examples. Since 93% of 30 is about 28, that means the model got 28 flowers correct and made only 2 mistakes. Let's take a look at the confusion matrix. The confusion matrix here shows what classes were predicted correctly and which ones were confused with one another. The correct predictions appear on the diagonal. The mistakes appear off the diagonal. For example, if the model predicts Versicolor when the flower was actually Virginica, that mistake shows up away from the diagonal. Let's visualize the tree here. We've designed the plot so it shows the actual structure of the trained decision tree. At the top, we have the root node, and that's the first question every flower has to answer. The tree checks one feature against a certain threshold, then sends the flower left or right depending on the result. Specifically, we're taking a look at petal length. If petal length is less than or equal to 2.45, we send it to the left leaf node. If it isn't, we go down to the next node right here. We're going to be checking whether the petal width is less than or equal to 1.65 centimeters. If it is, then we send it down here and we classify as Versicolor. If not, then we go down the right node, and then we land on the leaf node where the class is Virginica. Now let's talk a little bit more about depth. The tree we trained used a max depth of 2, which kept the model simple. But what happens if we let the tree grow deeper? We can see right here that the max depth was 2. You can see that we removed the max depth argument. Let's run this. Here we see a very high training accuracy. A deeper tree often gets this very high accuracy because it can split data into smaller and more specific groups. That sounds good at first, but it can become a problem if the model starts memorizing the training set instead of learning a pattern that generalizes to new pieces of data. And that's the phenomenon called overfitting. A tree that overfits may perform extremely well on training data, but worst on test data. And that's why we don't automatically choose the deepest possible tree. And here's where random forest could help us with. It helps with this issue by building many trees and then combining the average of the predictions. One tree might overreact to a small detail in the data, but a group or forests of trees can average out some of that instability. Here we have a loop that trains several trees with different maximum depths. For each depth, we train a new model and record both the training accuracy and the testing accuracy. As the depth increases, training accuracy usually goes up because the tree has more flexibility and more power. Testing accuracy may improve at first, but at a certain point, deeper trees really can stop helping, and that's through overfitting. More complexity can help with our trees, but only up to a certain point. Here we see at max depth 4, we've already reached the maximum test accuracy. By adding more depth, there is no improvement in the test accuracy. Here we'll also take a look at the training and validation accuracies. If training accuracy keeps rising while testing accuracy stays flat or drops, the model is probably becoming too specific to the training data, and is thus overfitting. And that's one of the main lessons from decision trees. A model should not only fit the training data well, it should also work on new data. Another way to control a tree is with a parameter called min samples leaf. The argument min samples leaf equal to 5 means each leaf node must contain at least 5 training examples. and that prevents the tree from creating tiny leaves for one or two unusual examples. Tiny leaves can make the model too sensitive to the training set. Larger leaves force the tree to learn broader rules. So now, we have two useful controls for our trees: max depth, which limits how deep the tree can grow, and min samples leaf, which limits how specific the final leaves can become. The next thing to take a look at is feature importance. Decision trees can tell us which features were most useful for making splits. A higher importance value means the tree relied on that feature more when separating classes. In the iris dataset, petal length and petal width often end up being the most important because they help distinguish the species well. Feature importance is useful, but it really shouldn't be treated as proof of causation. It tells us what the model used for prediction and not necessarily what causes the species to be different. In our decision tree, the most important feature here was petal length, and then the next most important feature was petal width. Here we see that sepal length and sepal width really wasn't needed by our decision tree. And here is the importance in plot form. Note that if one or two features dominate, the tree may be relying mostly on those specific measurements. That can make the model easier to explain. Here, our model is basically just relying on the petal length and widths. But it can also make the model sensitive if those measurements are noisy. And that's the basic decision tree workflow in Python. Here, the big takeaway is that decision trees are models that will learn through questions. They split the data, create branches, and then eventually reach predictions at the leaves. Once that idea makes sense, random forests and other tree-based models become much easier to understand because they are built on the same foundation. Thanks for watching, and I'll see you guys in the next video.